So as a recall, we are going at the page 24. Page 24. Last week, we have talked about the chi-square distribution. The chi-square distribution is a PDF. Okay, so I'll pronounce this chi, chi as chi. So more like a kai. Okay, chi-square distribution PDF with v degree of freedom. And then let's take a look at its domain. It is a positive number, but however, it is defined for the whole real number, the domain for the whole real number. It is just that while x is smaller than 0, then its probability density is 0. And when x is larger than 0, then its probability function looks like this. So let's just go slower a little bit and take a detailed look at this PDF. The probability density function has a 2 to the v over 2, then multiplied by a gamma function. And that gamma function is gamma of v over 2. And then x is the argument for the function. And then there's an exponent over here for 1. Let me see. For this minus 1 over 2x. Okay. And its notation is chi-square v. Okay. And let me just emphasize a little bit. Last week, people there are people asking me about how come there is a subscript at here, this subscript. So let me clarify a little bit. This subscript is just a notation, So that's when you write down f of subscript 1. That means the function, the first function. So it's just a notation. It has no mathematical meanings. This subscript has no mathematical meanings. And also, please do not see this square as a like an exponent. It's not exponent. This whole thing is just a, a, a symbol, a notation for this probability density function. Okay, so let's clarify this so that you don't get confused. Do not confuse this as a, although we pronounce it as a square, but there is no square here. Okay, it's not mathematically a square, a degree square. No, it's not that. Okay, and then the degree of freedom v is assumed to be an integer for values larger than 1. And then the gamma function is defined this way. Okay, let me just let me just be slower so that you get to read it. Okay, so this is the gamma of u. U is actually it's a dummy variable. It's like you have a f of x. You can do f of x and you can do f of y, and if you like, you do f of z. Whatever it is, it's just a dummy variable. Okay, this is a dummy variable. And then there's the integration. And like I said in last class, when something is written in an integral form, that means it has no closed form. If it has a closed form, we'll be happy to write it down. So there is no closed form. Okay, there's no closed form for this gamma. I'm sorry. It's just how come? Well, let me just use this. So, sorry. So we're going to just be patient. Okay. Uh, Let me see. Just wait a second. Wait a second. I think I need to change the settings a little bit. Okay. Yeah, that'll be easier. So now we are at page 25. Page 25. Right. No. Page 25. Let me zoom in a little bit. Okay. Then the gamma function can be written in this iterative form, which is gamma of u equal to u minus 1, gamma u minus 1. So if you have, let's say you have gamma of 5, then you plug it into this equation, you get gamma of 6. You get gamma of 6, you get gamma of 7, so on and so forth. You get a lot of things for this argument as as an integer. And in fact, this when n when this n is an integer, then that gamma is a factorial n minus 1 factorial. Okay, yeah. And then let's take another look. Let's take another look. You can see that this v equal to 1, we have this. V equal to 2, we have this. V equal to 4, 6, 8, so on and so forth. Then it will when v gets larger, then it becomes more and more like Gaussian distribution. Uh, in fact, in fact, the chi-square PDF arises as the PDF of x where x equal to summation of this x squared for x distributed as Gaussian distribution 0 and 1, which is a standard Gaussian. We call it standard Gaussian. Okay, and let me see. No, just a test. Okay, yeah, standard Gaussian. Let me see. I think it's okay. We will just go it. We'll just go this way. Okay. Um. So when you have a standard Gaussian, and then you sum the square of the standard Gaussian. Of course, they have to be IID. Okay, IID, and then you get chi-square. And as you know, if a lot of IIDs are summed together by this central limit theorem, recall central limit theorem in probability or statistics class. When you sum a lot of IIDs, they actually approaches a Gaussian distribution. Okay, so this is no exception. This is just like central limit theorem. Okay, uh, so then let's go to the next step. When we talk about uh, Gaussian, not Gaussian. When we talk about uh, a distribution, we are always curious about its mean and variance. So here, its mean is like this, and then variance is like this. Okay, and then A specific case of interest is when v is equal to 2. When v is equal to 2, then that distribution, this distribution, you can plug v equal to 2 into it and then do some simplifications. You actually get this exponential distribution. So we call it exponential PDF. And then the right tail probability is defined as the P. Remember, this P is the original P here, the original P, okay? And then you have a Q chi-square distribution, and then you integrate it from x to infinity. That's the right tail, and then it can be shown to be in this form for v even, okay? And now we go to page 26. Then for v arc, we have this form: q of chi v square x equal to 2q of square root of x for v equal to 1. Then if v is larger than 3, then it's 2q of square root of x plus this thing, and then summation of this. And if we take a look at the arguments inside, this is the square root of the x, which is fine, and this is the pi, and v and k. Then you will wonder, what is the k, right? K is the index for summation, so that is defined here. But after the summation, the k would disappear. And then in the MATLAB, you can use q chipr2. This is chi-square distribution, and then you can numerically evaluate this. All right, and then the next thing is chi-square for non-central. Let's see what's going on for this non-central. How come there will be one chi-square, as we discussed, and then we have this chi-square, and with the additional description for non-central. Okay, let's take a look. Sorry. I'm sorry. It goes messy. Okay. This chi is non-central. So when we are talking about this non-central, we are talking about x equal to this summation of xi square. But this I square is what? It is the standard deviation. Maybe I think I should call it variance. Variance equal to 1. And then its mean is non-zero with mu I. Okay. Then what's going on here? Let's do a comparison with this non-central, with this version. When we are talking about chi-square distribution, we are talking about summation of x square. That is zero mean. Okay, that is zero mean. So I like to emphasize there is this zero mean for the Gaussian random variable. But here at page 26, when we're talking about non-central, we have this x as non-zero mean, non-zero mean. So this is we call it a generalization of chi-square PDF arises as a result of summing the squares of IID Gaussian random variable with non-zero means. Specifically, if x is equal to this thing, x size I'm sorry, let me make a correction. It's independent. We should not say IID because IID means identical and independent, but there's only independent here. We don't have identical because their mu i's may be different. Their mu I, their mean may be different. Okay, so we should not say these xi's are IID. They're just independent, no identical. Okay, then x, which is this summation, has a non-central chi-square PDF with v degrees of freedom, and that v is the summation of the whole thing. Okay, and then non-centrality parameter lambda equal to this v mu I square summation. So you take the mean out of it, you take the square, you do the summation, you get this lambda non-centrality parameter. Imagine that when will you encounter this kind of random variables? You recall your undergrad classes when you are doing DSP class or communication classes. What do you encounter? We often encounter signal energy. Remember that? Do you remember that? The signal energy. When we are talking about signal energy, we take the signal x and then take the square, right? Then if the signal is Gaussian, then we have Gaussian square as the energy. So that's one example of what time and when do we encounter this chi-square distribution. That's when we have signal energy. And of course, there could be examples in other areas. So for example, in power systems, when you're talking about the energy of a power, or in image processing, you could have chi-square distribution. Okay, so I'm saying that this is very often. This is actually very often. We practice this in many engineering problems. Okay, then the PDF is complicated, and then we'll write it out here. Okay, we'll just write it out here. Okay, okay, so let's take a look at the PDF. The PDF is P of X equal to this, and it has this, of course, it's just 1/2, a constant, and then lambda over, no, make a correction, x, which is the argument, over lambda. This lambda is non-centrality parameter lambda, and then to the v minus 2 over 4. V is defined. Okay, V is defined. It's the degree of freedom, which is also the number of Gaussian random variables to be summed, to be to be summarized. Okay, and then exponential function of this thing with the x, which is this x, and lambda, again, the non-centrality parameter, and this I sub v over 2 minus 1 of this square root of lambda x. Then I is what? Let me just tell you a way of thinking about mathematical formulas. When you first time look at a, a function, you should take a look at the parameters inside the function, the formula, and then start to think about the definition, whether or not all symbols in that formula is defined. If it's not defined, then there is a problem. The function is undefined. So we have to clarify every parameter in here, and then eventually we find out that each parameter is well defined. So now I is not defined, right? I is undefined. So we are defining the I here. I sub r of u is the modified Basel function. And this modified Basel function, uh, we will call it spatial functions. And in fact, if you just try to search the keyword Basel functions, you have a lot of sorry, let me make a correction. If you search the keyword spatial functions, you find a lot of spatial functions. Some of them are simple and some of them are so complicated. Okay, and how come we have these spatial functions? Because in some situations, in many engineering problems, we just don't get close form. We don't get close form. As a result,